This stone looks completely ordinary, neutral color, no glow, no fire. Now watch what happens when the light changes. It transforms. Not because it's treated, not because of editing, because of structure. Most people think gemstones are decorative. They're wrong. Some gemstones split light more violently than diamonds. Some store ultraviolet radiation and release it later. Some change identity depending on the direction you look at them. And one of them, the stone at number 1, does something that feels almost impossible for solid matter. This is not mythology. This is physics under pressure. 10 stones, 10 lighting conditions. No exaggeration, just light colliding with crystal. Before we begin, quick question. When a gemstone changes under light, is that beauty or behavior? Let's begin. Ranked 10th, Enstatite. The stone that hides its light until the angle is perfect. Enstatite does not demand attention. It does not flash like opal. It does not split into fire like Sphalerite. It does not glow under ultraviolet light. And that is precisely why it earns a place on this list. Under neutral lighting, Enstatite appears restrained, earthy brown, muted olive, sometimes with a bronze undertone. It looks geological, grounded, predictable. But introduce a narrow beam of directional light, and something subtle begins to move. A fine metallic sheen drifts across the surface. Not glitter, not sparkle. A soft, sliding reflection, almost liquid. This effect is caused by microscopic lamellar structures within the crystal. Extremely thin plate-like inclusions align in such a precise internal order that light reflects in sheets rather than points. Instead of scattering, it glides. The result is what gemologists describe as a Schiller effect. But that technical term does not fully capture the experience, because what the eye perceives is motion. The light appears to travel. And here is where it becomes interesting. The movement is not inside the stone. It is not on the surface either. It exists at the boundary between structure and angle. Change the angle by just a few degrees and the sheen vanishes. That disappearance is the real phenomenon. Many gemstones perform under light. Enstatite withholds performance until precision is achieved. It rewards patience. Collectors often overlook it because the effect is not obvious in display cases. Retail lighting rarely reveals its personality, but under controlled directional light, especially a single-point source, the internal architecture becomes visible. It is a reminder that not all optical events are dramatic. Some are structural whispers. Enstatite belongs to the orthopyroxene group, a mineral family more associated with meteorites and mantle rock than with jewelry showcases. In fact, significant enstatite crystals have been identified in certain stony meteorites, linking this material to planetary formation processes. That geological heritage adds another layer of depth to what seems, at first, understated. And here is a subtle question worth considering. How many stones are dismissed simply because they require better lighting? Pause on that for a moment. In gemology laboratories, when evaluating subtle optical phenomena, experienced graders often rotate stones slowly under a tight fiber optic beam. Enstatite responds beautifully in that environment. The sheen does not shout, it breathes. There is something compelling about a gemstone that refuses to perform on demand. Perhaps that restraint is what makes the reveal more satisfying. If a moving band of metallic light appeared across a stone that looked completely ordinary seconds earlier, would that qualify as unbelievable? Or does unbelievable only count when it is loud? Curiosity often begins with stones that do not behave as expected. An enstatite, under the right light, quietly breaks expectation. In the next experiment, the transformation will be far less subtle. But before moving forward, which type of light behavior is more fascinating? Dramatic color shifts or these almost invisible structural movements? Leave a comment with subtle or spectacular. The pattern in those answers may reveal more about perception than about gemstones. Ranked 9th, Kornerupine, the stone with more than one identity. Kornerupine appears controlled, muted green, olive brown, sometimes with a faint golden undertone. It rarely announces itself, but rotate it under a fixed beam of light, and it refuses to remain the same stone. This is not simple color variation. This is pleochroism. And in high-quality Kornerupine, it can be so strong that the gem displays entirely different personalities depending on viewing axis. From one direction, deep forest green. Rotate slightly, earthy bronze. Shift again, yellowish olive. 3 identities, 1 crystal. The reason lies in its orthorhombic crystal structure. Light entering Kornerupine does not travel uniformly. It interacts differently along separate crystallographic axes, absorbing specific wavelengths in one direction while allowing others to pass in another. The eye does not see one color. It sees whichever version of the stone the light allows. And here is where it becomes psychologically compelling. Unlike dramatic color change gems that require switching light sources, Kornerupine changes while the light remains constant. The transformation depends on orientation, not illumination. That subtle distinction matters because it challenges the assumption that light alone controls perception. Sometimes structure controls perception. Under a jeweler's loupe, when the gem is rotated slowly, the shift can feel almost cinematic, like a scene adjusting filters in real time. This is why experienced cutters pay close attention to axis alignment. A misaligned cut can mute the effect. A precise cut can amplify the stone's internal duality. Historically, Kornerupine was often overlooked or misidentified due to its resemblance to more familiar greenstones. Only under proper examination did its optical complexity become obvious. There is something intellectually satisfying about a gemstone that reveals itself only through movement. It does not change because lighting changes. It changes because perspective changes. And that may be the more unsettling phenomenon. If a gemstone can alter its visible identity simply by rotation, how stable was the original color to begin with? Consider this quietly. When evaluating any gemstone, how often is it viewed from only one angle? How many conclusions are made without rotation? Kornerupine forces patience. It rewards examination. It refuses to be summarized in a single frame. For collectors who appreciate optical depth over flash, this mineral offers something far more refined than spectacle. It offers complexity, and complexity under light can be more surprising than brilliance. Before moving forward to a gemstone that reacts far more aggressively to ultraviolet exposure. A question for careful observers. Which is more intriguing? A stone that changes when light changes, or a stone that changes when perspective changes? Comment with light or angle. The distribution of those answers may reveal how perception is shaped long before physics enters the conversation. Ranked 8th, Scapolite, the stone that glows when it shouldn't. Scapolite rarely makes headlines. It does not dominate auction catalogs. It is not the centerpiece of museum exhibitions. Under daylight, it appears calm, often honey yellow, soft violet, or pale champagne. Nothing about it suggests spectacle, and then the ultraviolet light turns on. Without warning, an ordinary-looking stone ignites in vivid color. Bright yellow can intensify dramatically. Some specimens emit a strong orange or pink fluorescence. What seemed muted seconds earlier now radiates with unexpected intensity. The transformation is immediate, precise, clean. This phenomenon is fluorescence, but in Scapolite, it can feel disproportionate to the stone's appearance. The reason lies in trace elements embedded within its crystal lattice. When exposed to ultraviolet radiation, electrons absorb energy, jump to higher states, and then release that energy as visible light. What makes Scapolite compelling is not the science alone. It is the contrast. In white light, it behaves politely. Under UV, it performs. And unlike gemstones that shimmer subtly or shift tone gradually, Scapolite reacts decisively. The glow is not a suggestion, it is an event. There is also something psychologically powerful about a stone that hides this ability. In display cases without UV sources, many viewers walk past it without pause. Under controlled laboratory lighting, it commands attention. This raises an interesting consideration. How many materials are judged solely by how they behave in everyday light? Gemological evaluation rooms are built around this exact principle. Change the lighting, change the information. Experienced graders never rely on a single illumination source. Daylight equivalent lamps, incandescent balance, and ultraviolet exposure all reveal different aspects of the same crystal. Scapolite demonstrates why. The glow does not originate on the surface. It is not a coating. It is not a trick of polish. It emerges from within the atomic structure itself, a response written into the mineral at formation, often deep within metamorphic environments where pressure and heat altered its chemical composition. When ultraviolet energy excites those internal activators, the response is visible proof of microscopic architecture. And here is where the effect becomes quietly astonishing. The light that appears does not belong to the stone. It belongs to energy absorbed and re-emitted. The gemstone becomes a temporary translator of invisible radiation. In practical terms, fluorescence can help gemologists detect treatments, identify origins, or distinguish similar-looking minerals. In aesthetic terms, it adds a hidden layer, an alternate version of the same object. So consider this. If a gemstone reveals an entirely different personality under a spectrum the human eye cannot normally see, which version is the real one? The one seen in daylight, or the one revealed under ultraviolet? Leave a comment with daylight or UV, because the answer may say more about perception than about mineralogy. In the next experiment, the light will not simply trigger glow, it will begin to fracture into something far more dramatic. Ranked 7th, Taaffeite, the stone that confused science under light. Some gemstones impress immediately. Taaffeite did something far more unsettling. It passed for something else. For years, specimens of Taaffeite were mistaken for spinel, cut, polished, mounted, and traded under the wrong identity. The confusion did not come from carelessness. It came from how the stone behaves under light. At a glance, Taaffeite resembles spinel in tone, often soft violet, pale lavender, or faintly grayish pink. Under standard lighting, the similarity is convincing, but introduce polarized light or rotate the stone carefully beneath a focused beam, and a quiet contradiction emerges. Taaffeite is doubly refractive. Spinel is not. That distinction sounds technical, but its implications are dramatic. When light enters Taaffeite, it splits into two rays traveling at slightly different speeds. The result is subtle doubling of internal facets when viewed at precise angles, a phenomenon gemologists detect using magnification and controlled rotation. The stone does not shout its difference. It whispers it, and that whisper changed classification history. In fact, Taaffeite was first identified only after a faceted gem, assumed to be spinel, displayed optical behavior inconsistent with its label. The discovery did not begin in a mine. It began in a finished gemstone examined under light. That detail matters, because it means Taaffeite revealed its identity only through optical testing. Under certain orientations, faint pleochroism may also appear, gentle shifts in tone as the gem is rotated. These changes are not bold. They require patience, but they are real. Light exposed what visual similarity concealed. There is something compelling about a gemstone whose defining characteristic is discovered only after it has already been shaped and sold. It forces a reconsideration of assumptions. How many materials look identical until light is analyzed more carefully? In professional gemology, tools like refractometers and polariscopes exist precisely because appearance can deceive. Taaffeite stands as a case study in why optical testing is not optional. Its rarity adds to the intrigue, far rarer than spinel, but rarity alone does not make it fascinating. What makes it remarkable is this: the difference between common and extraordinarily rare was invisible without light behaving in a specific way, and that difference was enough to create an entirely new gemstone category. Pause for a moment on that idea. If two stones look nearly identical in everyday lighting, but light reveals a structural difference invisible to the casual observer, which one would most people choose? Comment appearance if surface similarity matters most. Comment structure if internal behavior under light matters more. Because Taaffeite proves something subtle yet powerful. Not all value is visible at first glance. Sometimes light must interrogate the crystal before truth emerges, and in the next experiment, the reaction will not require magnification. It will happen boldly, with a transformation that even untrained eyes cannot miss. Ranked 6th, Painite, the stone that changes character when light hardens. Painite appears restrained, a deep reddish brown, sometimes brick-toned, occasionally carrying a muted orange glow beneath the surface. It does not explode with fire. It does not glow under ultraviolet. It does not project brilliance across a room. And yet, under intensified lighting, something subtle but undeniable begins to shift. Increase the brightness, tighten the beam, rotate the stone slowly. The color begins to clarify. What seemed opaque becomes more translucent. What looked brown starts revealing flashes of crimson and red-orange from within. Under certain angles, a faint pleochroic shift may appear. Small variations in tone depending on orientation. Painite does not transform dramatically, it refines. And that refinement is what makes it extraordinary. The reason lies in its complex borate crystal chemistry, combined with trace elements that influence how specific wavelengths are absorbed. Under softer ambient lighting, much of the red spectrum is suppressed by internal absorption. The stone appears darker, heavier, but under stronger, focused illumination, especially balanced white light, deeper red tones can emerge as more photons penetrate and reflect internally. It is not a trick of polish. It is not surface reflection. It is internal filtering. The gemstone behaves almost like a selective gatekeeper of light. Historically, painite was once considered the rarest mineral species on Earth. For decades, only a handful of crystals were known. That reputation alone drew attention. But rarity is not what earns its place here. Its place is earned because its true color does not fully reveal itself in casual lighting. Under showroom illumination, it can appear subdued. Under laboratory intensity, it becomes more alive. This creates a fascinating tension. How many viewers would walk past it in a display case? How many would reconsider it after seeing it under stronger directional light? There is something almost philosophical about a gemstone that responds not by changing identity, but by clarifying it when examined more intensely. Unlike stones that react instantly and dramatically, painite demands better conditions. It rewards scrutiny. That makes it particularly compelling for an audience that appreciates subtle scientific phenomena over spectacle. Because what is more surprising, a stone that turns neon under UV, or a stone that quietly deepens into a richer red as light grows harsher? Painite challenges the assumption that transformation must be dramatic to be meaningful. Sometimes the unbelievable is not loud. Sometimes it is controlled. Before moving forward to a gemstone that fractures light far more aggressively. Consider this. When evaluating something rare, is the first impression enough, or does intensity reveal truth? Comment, first look, if initial color defines value. Comment under pressure, if stronger light changes everything. The next experiment will not be subtle. Ranked fifth, Diaspore, the stone that argues with the light source. Under daylight, Diaspore can appear soft green, balanced, natural, almost understated. Place the same stone beneath warm, incandescent light, and that calm green can shift towards champagne, peach, or even a warm pinkish tone. Nothing about the gem has changed, only the light has. But here is where Diaspore becomes more complex than a simple color change stone. It does not just react to the type of light. It reacts to the balance of wavelengths inside that light. Daylight is rich in blue and green energy. Incandescent light leans heavily toward red and yellow. Diaspore's internal chemistry selectively absorbs and transmits these wavelengths differently, causing a visible transformation that feels almost deliberate. The result is not abrupt, like some dramatic chromatic shifts. It is fluid, gradual, a negotiation between spectrum and structure. And then something even more subtle happens. Rotate the stone. Diaspore is also pleochroic, meaning it can show different colors depending on viewing axis. In certain cuts, three-directional tones can be observed: greenish, yellowish, and sometimes pinkish-brown. That means two forces are operating simultaneously: the spectrum of the light source, the orientation of the crystal. Few gemstones create that layered interaction. Change the bulb, the color shifts. Keep the bulb. Rotate the gem, it shifts again. This dual dependency creates a visual experience that feels unstable in the best possible way. The gemstone never seems entirely fixed. For gem cutters, alignment is critical. If the orientation is wrong, one color may dominate and mute the others. If aligned precisely, the stone appears dynamic even in stillness. That dynamism is not theatrical, it is structural. Diaspore forms in metamorphic environments under specific geological conditions, often associated with aluminum-rich rocks. Its crystal structure governs how light vibrates within it, splitting and filtering wavelengths differently along separate axes. The gemstone does not decide its color, it reveals whichever color the physics allow. There is something quietly profound about that, because it means the stone is not one color, it is a system of possible colors, and the viewer only sees whichever version the light permits. This raises an intriguing question. If a gemstone's appearance changes based on both the light source and its orientation, which version represents its true identity? Comment source if the light determines the stone. Comment structure if the crystal determines the stone. Diaspore refuses to give a simple answer. And compared to the previous stones on this list, its transformation is becoming less subtle, more visible, more undeniable. In the next experiment, light will not just shift tone, it will begin to fracture into something far more explosive. Ranked fourth, Sphalerite, the stone that splits light more than it should. At first glance, Sphalerite can look almost too warm. Honey orange, deep amber, sometimes leaning toward red-brown. It does not carry the cultural prestige of diamond. It rarely appears in mainstream jewelry. Its softness limits everyday wear. And yet, under strong, focused light, Sphalerite does something that feels almost unfair. It fractures white light into spectral fire with astonishing intensity. In gemology, this phenomenon is called dispersion, the separation of white light into its component colors. Diamond is celebrated for it. Marketing has built empires around it. But Sphalerite, in many cases, disperses light even more dramatically. Blue flashes, green sparks, red streaks, not scattered randomly, but erupting from within. The reason lies in its exceptionally high refractive index combined with strong dispersion values. When light enters the crystal, it slows significantly. Different wavelengths bend at slightly different angles. The greater the separation, the stronger the visible fire. Under a pinpoint LED or halogen spotlight, a well-cut sphalerite can appear almost volatile, as though the stone contains fragments of a prism trapped inside. And here is the striking part. Most viewers do not expect this, because Sphalerite is not positioned in the public imagination as a brilliance stone. It lacks the branding of diamond, the myth of opal, the drama of alexandrite, which makes the moment of illumination even more disruptive. There is something psychologically powerful about a material outperforming expectation. Under low light, Sphalerite appears rich but quiet. Under strong directional light, it becomes electric. This performance is not subtle. It is not interpretive. It is visible even to untrained eyes. However, there is a reason it does not dominate fine jewelry markets. Its relatively low hardness makes it vulnerable to scratching. It is a stone of display and admiration, not daily endurance. And that limitation adds another layer to its story. Sometimes extraordinary optical behavior exists outside mainstream attention simply because practicality intervenes. If value were based purely on light performance, Sphalerite would rank far higher in public awareness. Pause on that thought. If two stones sit under the same spotlight and the lesser-known one produces more fire, which one deserves the attention? Comment, performance, if optical behavior defines greatness. Comment, reputation, if legacy still matters more. Because Sphalerite challenges a comfortable assumption. Fame and physical performance are not always aligned, and as the list continues upward, the transformations will shift from explosive fragmentation to reactions that feel almost unnatural. The next gemstone will not just split light, it will glow with a presence that seems to defy its quiet exterior. Ranked third, Tugtupite, the stone that turns pink in the dark. Under ordinary lighting, Tugtupite can look deceptively calm. Soft white, pale pink, sometimes carrying faint gray undertones. It does not announce itself as dramatic, but remove visible light and introduce ultraviolet. The transformation is immediate. A vivid, almost neon pink erupts from within the stone. Not a surface reflection, not a faint shimmer, a saturated internal glow that appears as though the crystal has been switched on. Unlike gemstones that merely reflect or refract light, Tugtupite actively emits visible color when stimulated by ultraviolet radiation. This is fluorescence, but in high-quality specimens, the intensity feels disproportionate to the stone's quiet daylight appearance. The source of this reaction lies in trace activator elements embedded within its crystal structure, often manganese. When ultraviolet photons excite electrons within the lattice, those electrons jump to higher energy states. As they return to equilibrium, energy is released as visible pink light. Invisible radiation becomes visible color. That conversion alone is compelling, but some specimens take it further. Certain Tugtupite crystals exhibit a phenomenon related to tenebrescence, a temporary color change that can persist after UV exposure. The stone may deepen in pink tone even after the ultraviolet source is removed, gradually fading back over time. It is as though the crystal remembers, and that memory is what elevates Tugtupite beyond simple fluorescence. Under museum lighting, the stone appears gentle. Under UV, it feels alive. The contrast between those two states creates a visual shock that even untrained observers recognize instantly. There is no need for magnification, no need for precise angles, darkness, ultraviolet light, and transformation. This dual personality is not theatrical mythology. It is structural chemistry responding to energy. Tugtupite forms in rare alkaline igneous environments, most famously in Greenland. Its geological origin contributes to its scarcity. But rarity is not what commands attention here. It is responsiveness. The gemstone does not merely interact with light. It converts invisible energy into something unmistakably visible. Consider the implications of that. If a material can glow intensely under a spectrum humans cannot normally see, how much of reality depends on wavelengths outside ordinary perception? Comment: hidden energy, if invisible light feels more fascinating. Comment visible change, if the glow itself is what captivates. Because Tugtupite demonstrates something profound. Light is not just illumination, it is activation. And as this list approaches its final two stones, the transformations will shift again, from reactive glow to optical phenomena that feel almost engineered. The next gemstone does not simply glow, it fractures light with precision that seems almost impossible. Ranked second, Benitoite, the blue stone that turns light into fire. Under soft daylight, Benitoite already looks unusual, a sharp sapphire blue. Clean, saturated, almost electric in tone, but increase the intensity, narrow the beam. Focus a single-point spotlight onto a well-cut stone, and the transformation begins. White light fractures into razor-thin flashes of spectral color, reds, greens, violets, scattering from a body color that is already vividly blue. The effect feels paradoxical, a blue gemstone producing bursts of multicolored fire that seem almost too strong for its size. This is extreme dispersion. Dispersion occurs when different wavelengths of light bend at different angles as they pass through a material. In most gemstones, this effect is present but controlled. In Benitoite, it is amplified. The refractive index and crystal structure allow for an unusually strong separation of wavelengths relative to its transparency and clarity. Under proper lighting, the flashes are not subtle, they are precise. And here is what makes the experience especially striking. The body color is already intense. In many high-dispersion stones, strong body color can mute fire. But Benitoite balances both. Deep blue absorption coexists with sharp prismatic flashes. The eye struggles to process both phenomena at once. It looks engineered. It is not. Benitoite forms under rare geological conditions involving barium-rich hydrothermal environments. Its natural crystals are typically small, which makes well-cut, high-clarity specimens even more visually concentrated when light enters. Under ultraviolet light, Benitoite can also fluoresce, often glowing blue, adding another layer of optical complexity. But it is under strong white spotlighting where the stone truly asserts itself. Rotate it slowly. The flashes leap unpredictably from facet to facet. Unlike Sphalerite's warm fire, Benitoite's dispersion feels colder, sharper. almost crystalline in precision. And this raises a compelling thought. If brilliance is measured by how effectively a gemstone manipulates light, should familiarity influence judgment? Comment diamond if tradition defines brilliance. Comment Benitoite if performance under light defines it instead. Because what Benitoite demonstrates is simple and disruptive. Light does not care about reputation. It responds to physics. And when physics aligns correctly, even a small, lesser-known crystal can produce optical performance that challenges long-established expectations. As the list approaches its final position, the transformation ahead will not rely on dispersion or glow. It will rely on something rarer, a gemstone that does not just react to light, it retains evidence of it. In first place, Hackmanite, the stone that remembers the light. Hackmanite can appear unremarkable, soft lilac, milky white, sometimes faintly violet. Nothing about it suggests spectacle. Nothing about it prepares the eye for what happens next. Turn off the visible lights. Introduce ultraviolet. The crystal deepens. Dramatically. Pale tones intensify into saturated purple. The shift is not gradual, it is decisive. But the true astonishment does not occur when the color changes. It occurs when the ultraviolet source is removed. The color remains. Seconds pass, sometimes minutes. Gradually, the stone fades back toward its original tone. Hackmanite does not simply react to light, it remembers it. This phenomenon is known as tenebrescence, a reversible photochromic effect in which exposure to ultraviolet radiation alters the crystal's electronic structure in a way that temporarily changes its absorption of visible wavelengths. At the atomic level, specific defects within the crystal lattice, often involving sulfur-related color centers, capture energy. These defects modify how light is filtered through the structure, deepening visible color. Over time, or with exposure to different wavelengths, the lattice relaxes, the original color returns. What makes Hackmanite extraordinary is not brightness, it is persistence. Fluorescent stones glow only while stimulated. Color change stones shift when lighting changes. Hackmanite carries the evidence forward. There is something deeply unsettling about that, because it suggests that light can leave a temporary imprint in solid matter. Not metaphorically, physically. This property has drawn interest far beyond jewelry. Materials scientists study similar reversible color mechanisms for applications in radiation detection, UV exposure monitoring, and smart materials that respond to environmental energy. Yet here it exists in natural crystal form, formed deep within geological environments long before human observation, structured in such a way that ultraviolet photons can rearrange its internal balance. The gemstone becomes a recorder of invisible radiation. And this raises a question that moves beyond mineralogy. If a crystal can hold a trace of light after the source disappears, how much of the physical world carries temporary imprints unseen by the naked eye? Comment memory if the persistence is what fascinates most. Comment change if the instant transformation is more compelling. Because Hackmanite does not perform for attention. It demonstrates a principle. Light is not merely illumination, it is interaction. It can alter structure, briefly, reversibly, but measurably, unlike dispersion, which dazzles. Unlike fluorescence, which glows. Unlike pleochroism, which shifts with perspective. Hackmanite records. And in a list defined by gemstones that do something unbelievable under light, this is the one that crosses into something more profound. It does not just respond, it retains. Under normal light, most of these stones look ordinary. Change the light, and structure answers. Some fractured white light into fire, some shifted identity with a simple rotation. One retained a trace of ultraviolet exposure itself. None of this is magic. It is physics inside crystal. If one experiment genuinely surprised you, comment the number, not the name. Because what people choose says more about perception than about minerals. And remember, a gemstone is never fully understood under one light source. Change the light. Rotate slowly. Look again.